Hello and welcome to another Matlab tutorial. In this tutorial I'll teach you about the Eulers method and how to solve differential equations using the Eulers method. In this example I will firstly explain briefly how the Eulers method works, and then I'll give you some example on why Eulers method might not be good for certain applications. And lastly, I'll show you how you can program an example that applies the Euler method to solve a given differential equation in Matlab. So, Euler's method is a method that you can use to solve differential equations, and these equations are in general first order differential equations that you can write as dy dt equals to some function of t and y. This function is known and written and defined by a certain system in practical cases. You can resume Euler's method as a discrete way of solving continuous time differential equations. So at each time step k, it follows these recursive equations. So the next value for y, so y of k, will be given by the previous value of y, so y of k minus 1, plus delta t, which is the time step, times the function that defines the derivative of y with respect to t, so f of t and y, computed at the instant t of k minus 1, so at the previous time step, and at the previous value for y. You can imagine Euler's method as a method that approximates the real solution of the analytical function with a tangent line. When you define the time step, it basically integrates the current derivative value and adds it to the previous y value and obtains the next y of k, as you can see here. As you can imagine, if you choose a large time step, the solution found by the Euler's method will deviate a lot from the real solution, and I will demonstrate this now. To demonstrate this then, I'll solve the differential equation that is characterized as dy dt equals to y, with the initial condition at t equals 0, y will be equal to 1. For this purpose, I'll use time steps of 1, 0.1, 0.01, and 0.001. In the first part of the code, I am defining the characteristics of the differential equation, so the function f will be an anonymous function in this case that is simply defined by the value y, so a function of t on y, and just y here. The initial value of y, so y at t equals 0 in this case is 0, will be 1, and I'll solve this equation from t equals to 0 from 5. And in a for cycle that will take as time steps 1, 0.1, etc. I'll solve the equation using the programmed function I've programmed in Matlab, and I'll show it later to you. And after that, I'll simply plot the solution found by the programmed Matlab function and the analytical solution, so we can compare the errors. So let's run this code. Okay. As you can see, for a time step or t-step of 1, the solution deviates a lot from the real solution. So now for a lower time step, as you can see, the function is getting closer to the real solution, and for an even lower time step, even closer, and for an even lower time step, and even closer, nearly matching the original curve. So as a rule of thumb, if you want to apply Euler's method, you should use a really small time step. The function that solves this differential equation applying the Euler's method that I've described previously is defined here. So this function, I've called it Euler, and takes as the first input the handle of f of t and y, the Tspan vectors. So this is a vector that in its first component contains the initial time step, and that in its second component and last component contains the final time step. This is the initial value of y, so at the initial time step, y will be valued at some point, the desired time step. So to initialize the time vector, t will be simply given by the first component of the vector Tspan, with steps of Tstep to Tspan of the second position or end. Then we'll Then I pre-allocated the y vector to make the function run faster. I've pre-allocated it using NaN values. And y will be a matrix if we're solving a system of differential equations that has an order bigger than 1. So, in other words, in the columns of y, there will be the corresponding t values. So the columns of y will span as t. So as you can see, the columns will have span of t. The number of rows contained in y will have the span of the initial condition. And again, as the initial value of y is known, I've set that in the y vector, the first entry, so the first column, will be equal to the initial y. After this, we simply need to apply the recursive Euler method procedure, and that can be defined with the for cycle that ranges for k equals to 2 to length of t, and this 2 appears because we already know the initial value of y, and this is the formula you've seen previously. So this covers everything I wanted to talk about the Eulers method. If you want to learn how to solve differential equations using ODE45, which is a very known Matlab function, you can check out this video I've made previously. Thank you very much for watching, and hopefully I'll see you in another tutorial.